All right. Hello, and hello. Yeah, I know I've got nothing up there right now. My apologies. Um, all right. So what we want to focus on today is going to be our algebra of logarithms, or kind of our rules of logarithms and logarithmic equations. And then we're going to kind of put all of the rules we did together and look at some models in general. So what I want to do here is I'm actually tried this. I'm going to try to put on the board here the rules of logarithms and then go from there. And so what we get is, if we look at our exponentials, and the rules that govern exponentials, they're going to have log equivalent forms. Not saying that it's related to the logarithm per se, but because exponentials and logs are inverse functions, these relationships hold a parallelism. Yeah, parallelism. That's the word to look for. That's all the good ones there. So log of any base of 1 is equal to 0. Log of any base of b is equal to log base b of b equal to 1. Log base b of m times n is log base b. Sorry if I'm not babbling as much as I write these. I want to get them up here first. I know I had these up before, and we used them to manipulate to get the change of base formula. We'll manipulate these on many different occasions. And our inverse relationships, if I take b and I throw into it the log base b of x, I get x out. And if I take log base b and throw into it b to the x, well, I get x out. And so both of these operations will give me x. And as I tend to say, this is our secret sauce. Right. This one here and these inverse relationships we tend to use to pull things out from exponents as we go through. So look at these, look at these, look at these, look at these. And what I'm going to do is we're going to look at the idea of expanding logarithms. And these are on page 458 in your book. The log examples of them, the exponentials. And if you remember, in the beginning of the semester I gave you a sheet that had rules in them. These were kind of two down over on the first page. You had these, and then these were in a little kind of rounded cornered rectangle. All right, so learn the rules, learn the rules. Well, let's do some things with them. Let's see why we're learning the rules, and we're going to move this back, but we'll work our way into some specific models in one particular model. And so how these properties go. So the first thing we want to kind of do is these things can be used for expansion. So now let me come over here, make sure I'm visible. I can be given a logarithm of two things. And, hey, my logarithm didn't make it up to you guys. Come back, logarithm. Why is that not showing now? What happened here? Let's see. Oh, there it is. Okay. You guys see log xy. It's here, I'll show you what happened with me, why I was worried. If you look at my browser up here in the live corner, it's hiding what I had written. And I thought you guys weren't seeing what I had written. Sorry about that. If I have a logarithm and it's given to me in this form, I might want to expand it back out. So I look at my rules and I can say, hey, multiplication turns into an addition. So notice inside the logarithm's getting this, and sometimes you'll see people write it like this to make sure that we can see that the log is getting those two terms. Your book isn't a big fan of using the parentheses, and so if we're multiplying anything by a log, we tend to put it in front of it. Now this log is log base 10, but it doesn't matter that this is log base 10. What's going to happen is this logarithm is going to split, and it's going to turn into an addition because of our rules. And I tend to think of this again as PEMDAS because logs deal with exponents. Multiplication, I have to look to the step below in PEMDAS, which is addition. And it breaks it apart into two clean logarithms. You'll see this is a good way for isolating variables. We'll use this to get variables to the place where we want them to be. As I look at a couple of log equations as we go through here. All right, well, let's kind of see how we can do these. I'll use another base here. I can have the natural log of, let's see, let's find one. Natural log of x divided by 2. Again, I have a division. I'm in my log space, so that expands as a subtraction. And I'm subtracting the upstairs from the downstairs, keeping each to the logarithm with the same base. ln2 appears a lot in things we do. It's roughly 0.69. Right? Natural log of 2 is a very common thing. So you might see that pop its way out a bit. So I'm pointing it out now. Natural logs of 2 are nice things to have. All right, and let's look at one more here. And our idea here is I am expanding. I'm taking it and I'm telescoping them out. Let's see. I will give log base 2 of the square root of x cubed over the square root of x. Now, here's an interesting thing, and it comes back to why I liked radicals to be expressed in terms of powers, and why I use the power notation instead. So the first thing I'm going to do here is I'm going to turn these into their power notation. So this becomes x cubed to the 1/2 power over x to the 1/2 power. And actually, for point of illustration, we're going to make this a y downstairs. I don't want to simplify these variables. The book uses the same variables, expands them out, where you could actually simplify it. So I'm going to use y 1/2. My apologies if we can just treat this. I want to be able to split them apart. All right, so I have a power, set of powers and a division. What I'm going to do is I'm going to keep working along here. Sorry, let me make lines between my different ones here. Things we call expansions. So I'm still going to have log base 2. And I'm going to apply my power rule. So that's x to the 3/2 upstairs. Minus, because I'm breaking it apart on the division, log base 2 of y to the 1/2. Right? I use my power rule here to bring these exponents together. I use the division to separate this logarithm into subtraction. Now I'm going to use my power rule, which tells me I can multiply this out front. And I'm going to do the same here. And this is called expanding logs. What we tend to do is we try to get this into terms, the easiest term of whatever variable we have. And this is usually to help isolate variables or isolate well-known constants like natural log of 2. Well, I'm going to switch colors here. I'm going to go to my lovely sky blue. These are reversible processes. Anything that has an equality, right? A equals, 4. If I have A, I could say, oh, that equals 4. But if I have 4, I can also say the opposite. It equals A. No side of an equation is better. For some reason, most people read them left to right. And I think we set a lot of formulas that way. But we can do the opposite. We can pull them together. So let's look at the natural log of 2 times z plus the natural log of 1 over e. Now notice I have 2 logarithms with the same base. So I can turn them into a multiplication. Let's see if I can go back here. All right. I'm looking at this rule from this side, and I'm moving over to this side. I'm starting here, going over to here. I have the same base, so I'm going to multiply the terms together. So I'm going to have the natural log of 2e times 1 over e. Well, the e's will cancel, and this gives me the natural log of 2. All right, I'll do another one that uses a natural log. I like my natural logs. 2 times the natural log of x minus 1/2 the natural log of y minus 3 the natural log of z. All right, so I'm going to look at the coefficients first. Again, I'm going to think I have something out in front of a log, so it's going to be able to come in and be the exponent. So this becomes the exponent. I have the natural log of x squared minus the natural log of y to the 1/2 minus the natural log of z cubed. So subtraction is division. So I'm going to get x squared divided by y to the 1/2 minus natural log z cubed, which is one more division. So I'll do my last division here. And I've simplified my log. Now I think your book will write this as what the square root of y. Again, I like the powers because we keep our power rules. And so we're able to manipulate our logarithms so that we can get everything inside the logarithm, so that we can compound the logarithm, and we can make them come together. Which leads us to that we can actually do equations with these things. In fact, most of the equations that we do with them came from our models. And I actually want to look at a couple models using equations. And I've kind of pointed out some of the better uses of this, right? If I have the natural log of something equals the natural log of something else, then I know A equals B. If I have the exponent of something equals the exponent of something else, I know that those two things are equal to each other. And again, these are reversible processes. And so our log algebra is really hoping that we can get one side in a log and another side in a log, so that we can get things together. Let's look at some equations that come out of these things. One I really want to show you. Let's see. I'll actually go to the exercises in the book because their examples are a little two steps. Right? And some of these can be slightly more steps. Okay, so let's look at some natural log algebra. And what we can do with it to remove them. So I'm going to take an example here. I have a log base 10 equals x squared plus 1. The log of x squared plus 1 equals, get my equal sign in the right place, 2. Now I have an x squared plus 1 stuck in this logarithm. So I need to get it out. And the thing that really helps me get things out of logarithms are these inverse functions. And so these inverse functions, if I take the base and have my logarithm be the exponent of that base, they'll cancel out, leaving me with the term of the logarithm. So when I have an equation like this, this is the common log, so that's base 10. So if I were to take the left-hand side, like that, I still have to do it to the right-hand side. Whatever I do to the left-hand side. And think about it. What I'm saying here is 10 to the x is equal to 10 to the y. Right? If I make my left-hand side x and my right-hand side y, they are equal to each other. So I can make them powers. So I make my left-hand side a power to 10, and I make my right-hand side a power to 10. Well, because these have the same base, they cancel. And I get x squared equals 99. X equals plus or minus the square root of 99, which, what is that? That's plus or minus 3 square roots of 11, I think. but and that and we're able to solve. So we can solve for x in our logarithms by using our properties to isolate x. And I hope you can see that the sneaky property I keep coming to is using the base, either with the logarithm or with its exponents, to bring it out. Let me look at, I want to find one. There's a particular version of this that happens a lot, that the book gives you an example of, and I have an example of it here that I want to work in the modeling. So I'm gonna look at some of the models and build out of the models this algebra. I think it might be better to do things that have meaning in this case, and that we're actually going to use particular models to focus on the algebra. So let's look at our growth and decay models. Now for my growth models, for a growth function, and I'm in time, and I have some original amount of substance of e to a constant times that time. And that k constant is the thing that determines the growth rate. Now for my decay models of t a naught e to the negative kt. And in general, you don't have to worry about what this sign is. Your data will tell you what the sign is. But if k is greater than 0, it's growth. And if k is less than 0, it's decay. And yes, I know, I'm repeating myself a bit. It's okay to repeat. This is fairly important for us. And so when we look at that our data is increasing, we'll look at this a to the ek. If we look at that our data is decreasing, we'll look to the e to the negative kt, especially if it's decreasing towards 0. And so I'll actually use this here. I'll go back to my graphing software. Let me just hide these for a second. Come back. I'm in a mumbly mood today. Sorry about that. Don't mean to be mumbling. I'll try to project myself a bit more. So E. The general behavior of both of these growth and decay functions are, if it's a decay function, it starts at 0, it has a value of 1, and decays down until it tries to get to 0. It'll never reach 0, but it tries to. If it's a positive k value, it starts at 1 and works its way out towards infinity, positive infinity. Now they both start at 1. And what this is telling us is that when the time is 0, this e to the kt, when t equals 0, is equal to 1. It's a multiplier. And the job of this part of the function kicks out a percentage or a ratio or some multiplier. So with negative decay rates, you get these declining. When is it at 0.5? When is it at 0.25? Because this keeps spitting out a different fraction as it gets closer and closer to 0. And for the growth models, the e to the kt starts spitting out 1 times, 2 times, but they're multipliers. These things multiply the original amount that you have. And so their job sets out to do that. So let's look at a couple models. And I really want to move towards the combined model, a logistic model. coming across. But instead of a logistic, let's look at really hate doing the same population models over and over again for the same radioactive decay ones. But they are fairly illustrative. Now I will do, because I want to do the equation, I will do a different population curve. Let me pull it here from the book. Drop back a chapter. Do log. There we go. Okay. So I'm going to do a half-life, and it's a link on Twitter, which a half-life of a link on Twitter is 2.8 hours. And so we can write a function that gives the percentage of engagements remaining on a typical Twitter link after so many hours. And so we estimate that the percentage, and so we want to estimate the percentage after 5.5 hours. So what we're saying is I put a link on Twitter, a Twitter link, and its engagement is going to peak and then decrease. And that decrease is an exponential model, is what we're going to model on from the peak, and it has a half-life. Right? And so that's what the problem's telling us, and that's what we need to work on, is figuring it out. So we have a decay rate, and a decay rate that's usually based off of returning values. And so what do we say the half-life is 2.8 hours. So I'll say the time to get half of my link engagement is 2.8 hours. So I can write a model that the amount of activity after a certain amount of time is equal to this peak amount, right? A peak. And that'll be when time equals 0. When we peak, e to the negative kt. Well, if I want to make this model predictive, I want to find k. And so k is the thing we're going to hunt. Well, we know that at 2.8 hours, that a is equal to 1/2 of the peak amount. So I can take this value and this value and plug it into our model. Right? This is our model. We don't have our constant for our model yet, but we'll find it. So 1/2 AP equals AP e to the negative k times 2.8. Whoops, that's an AP. Said it, but it didn't write it. Again, these will divide out, leaving 1/2 equals e to the negative k 2.8. Notice, because this is a multiplier and it's spitting out a fraction, and a half-life is telling me a multiplier of an answer, the initial amount doesn't matter. The fractional part, the percentage part, is all that matters. And I think that's the secret to most of our models with exponentials. It is finding that part that spits out. All right, so I'm going to take the natural log of both sides. Because my variable is in an exponent, and so I want to use the base, and since this base is e, I'll take a natural log of it. And going to my rule, these will cancel each other out, give me negative k times 2.8. Well, on this side, I'm gonna think of 1/2 as 2 to the negative 1. So this is negative ln 2. All right, 2 to the negative 1. I can pull my power out front, and I have ln 2. The negative signs will cancel. And k is equal to ln 2 divided by 2.8. So I have created my model and using my exponential and logarithmic algebra to move it about. So let's finish our model out here. I have whatever my peak amount is. My amount of engagement is my peak amount as a function of time, e to the negative, and I'm going to approximate this to a few decimal places. So ln 2 divided by 2.8 is 0.2476 times t. And so now I have a model. And I think the question was, we have our model, we have our half-life of engagement. What will be the engagement after 5.5? What percent will be the engagement after 5.5 hours? Well, if we're focusing on percent, right, we can think of AP as 1. Right? 1, which is our statistical way of writing 100%, I guess. And so we can think of our amount then being after 5.5 hours, e to the negative 2.476 times 5.5. My decimal place in there, right? Notice how getting the model, the setup for the model, takes most of the mental activity. Once you have the model, it falls into that realm that you'll sometimes hear people say, plug and chug, right? You've generated your formula, and now you plug values into your formula to see the outputs. And so I think they used 1 decimal place, so about 0.26 percent, or 26% will survive. You'll have that engagement level that after 5.5 hours. Sorry, I do think of them as survive or disperse. I try to use the words coming through. All right. This algebra skill and the things that we use with logarithms and exponentials really accumulates into modeling, and it is some of the most effective modeling that we have. Exponentials have a thing in calculus where they're their own derivative as a function. Because of that, because they're their own derivative as a function, they end up being a very easy thing to plug into equations that have derivatives. And so loads of equations that we have, e to the power of something is the best answer. And it's a flexible answer. And I hope you can appreciate, with the right choice of a k constant, we can use an e to a power instead of a 2 to a power. There is a particular set of solutions called logistic equations that combine kind of the two things we were looking at. And so I'm going to say they're called a logistic equation. And I'm going to use this to hone our skills on our algebra, right? This is kind of like everything we have done this semester, accumulating into using our logarithms and our exponentials would be the logistic equation. So let me draw what a logistic equation looks like and explain its usefulness. I'll then use an example that might not appear as useful, but it's calculable. All right, so that's time. And this is some amount of stuff. Usually it's a population, but it's some amount of stuff. So this is 0 in amount of stuff, and this is 0 in time. Now, I can start with a given amount of the population. I can start with so many of the animals, and let me use the animal. We'll use a predator prey. I first introduced this particular equation in a deer species in Pennsylvania, because with building of houses in Pennsylvania, declining areas for the deer to eat, so their food sources go down. But deer tend to breed on an exponential curve. So what ends up happening is deer want to increase in population, and they will. They'll do what deer do. They'll go out, mating season will come around, there'll be more deer, they'll grow, and the population will grow until food becomes scarce. At that point, the survival rate to mating season starts to go down. And so they don't grow anymore, and they actually start to decay. And so you have a competing growth and decay curve making logistic curves. And what they end up having in them, and they can have multiple lines like this, but in general, they tend to have a individual line that usually gets called the carrying capacity. And it's whatever the value of P is, I'll call it PC here, that the environment can sustain at equilibrium. The amount of growth is equal to the amount of decay. So for the deer population, the new deers being born is equal to the deers dying. And so the amount of food is enough to match what is coming in. And so if you I've seen this, another good example, salmon farming. The water can only hold so much of the animal, can only feed so much of the animal, can only physically house. So this carrying capacity becomes a way of defining the whole environment the species is in. And it lets you know how much resources in the environment can produce more species. So if you put more species in, then, I'll do this in red, then what it can carry, it'll do an exponential decay. And then it will get to its carrying capacity, and it'll stay out. And so over time, the population will die down. And it will come down. So, but if you put in more than what the environment can handle, it will decay gracefully down towards it. Well, not gracefully, it's probably fairly traumatic for this salmon that you've tried to overpopulate in the salmon farm. If you start with less than what the environment can carry, it will begin an exponential growth curve, and then the environment will start limiting the rate of growth, and it flattens out to the carrying capacity. And these logistic curves from the lower end kind of have a growth side and then a flattened growth. And so when I was talking about the population models earlier, I was being very idealistic to say that they always grow, right? There is a time period here where we can model this as exponential growth. And there's a small time period in here where I can model it as that. And a lot of people will see that side of the data and they're like, well, exponential growth will end up going up this way. But most environments, most resources have limits. They have carrying capacities. And so the logistic equation actually is probably the most realistic model we can be approached with. And I think you can see already it's a fairly complex one. Let me pull up a better logistic graph here. Though I'm quite happy with my drawing today, can do better. So here's an example logistic curve. It has this part that's almost exponential right in here, and then it flattens out. And so if we compare it to an exponential growth, there is this place early on in the curve where they overlap, and it looks like it's exponential growth. And then the logistic curve pulls away because the environment can't support that level of growth. If we compare it with a decay, right, we can kind of think of subtracting these two curves from each other gives us the logistic curve. But it's a little more complicated than that. And we're going to look at this. And the book has a good example of logistic curves, and we're going to work through one. It's a realistic model, and you should appreciate realistic models, because if you ever work with environmental units, within anything that needs a resource to sustain its reaction, these are very similar to titration equations within chemistry. This model can be applied to many things. I was taught it initially environmentally, and so that tends to be the model I go through because it's one of the easier things to see. I'm actually going to show it to you in a business model. Now let's see. I'm going to need a new blackboard here. So, oh no, I might. No, this is long. This is going to take everything we need to do. So I'm going to clear this blackboard off. While I clear the blackboard off, look at the rules of logarithms. Look at them. They're nice rules. These rules help us. These are the rules of logarithms. Exponents are on the left, but the logarithms are neat. We knew the exponent ones from before. There, I cleared the blackboard, and you got to look at the rules of logarithms. All right, so I'm going to make the equation that models the logistic equation, and we're going to use it. And we're going to use it in a particular model. So first, all logistic equations have a form, and I want to use the same variables the book has. You have your output, whatever you're measuring, as a function of your variable. It's usually time, is equal to, I want to get my variables right. There are three variables we need to set in the logistic equation. Yeah. So I'm going to make this a capital A. So it is clearly not one of the lowercase letters I'm going to use in the equation. There is some C, which is the carrying capacity. And we're going to have 1 plus some amount times e to the negative bt. And this is that logistic model. And so when you see a logistic model, what you're going to see is your data starts growing quickly and then slows down. And that's a logistic. What it's showing is you have something that wants to do exponential growth, but it's being balanced out by its decay rate or limited resources. And so C represents the carrying capacity. Because if t were to go out towards infinity, if time keeps going on, this would approach 0. And if this approaches 0, I get C over 1. And that's the carrying capacity then. And so C represents the carrying capacity. A and B reflect A is related to how much stuff you start with, your starting population. But it's not really like a starting population you can plug in. It's kind of a ratio to that. And then in this reflects your rate of change. Just like the K constant was kind of a rate of change. A measure of how this was changing. All right, so let's look at an example. Let's look at what the data looks like of this. And this is going to do multiple things for us. We're going to dig into a logistic curve. We're going to dig in with something that has a carrying capacity, a real life environment that has an exponential process where it wants to zoom off, but there's a limited amount of resources. Finding these three variables is hard. So we're going to have to use all of the skills we've learned all semester in this one thing. Which is usually that's the last thing I talk about, because we need to use everything. So here's the data I'm going to get. This is cell phone usage in India, or cell phone ownership in India. So cell phone ownership in India. What I'm going to do is I'm going to have a year and the number in, let me get it right, billions. So this is the number of cell phones in billions. Cell phone subscriptions. And so we start at 2004. No, 2005. Ooh. I almost gave it year. All right. And we go up to 2011. And let's see, we have 0.05 for here. We have 0.12. 0.21. 0.2140. 0.60, 0.75, and 0.85. And so here's the data. All right, so if I were given this as a problem to make some model to predict future, right? So that's what we want to do. We want to predict future cell phone subscriptions or service, right? Because if you're building all the towers, you need to know what your tower, how much tower you're going to need, how much network space you lay down for each tower. You're going to need to know what your future data requirements are. You need your future infrastructure requirements. So you need a good predictive way of looking at the data. Now, we could think exponential growth. Every business person wants to think exponential growth until they have to pay for the infrastructure for it. Because exponential growth means that you would have an infinite amount of resources eventually, right? Money coming in. But we know there could be some limiting factors. There's only so many people. And there's only so much money that people can bring to bear. So there's probably a carrying capacity. Now, would the carrying capacity show up in our equations or in the time frame we're looking at becomes the big question. And so let's look at our data. This jumps by 0.07. This jumps by 0.09. This jumps by 0.19. 0.20. 0.15. And 0.1. So notice the amount that I'm gaining speeds up
and then slows down. So the amount that I'm gaining speeds up and then slows down. And so this is a logistic model. All right. So to get our logistic model, we have three variables, C, A, and B. The rule of thumb in equations, not even a rule of thumb, it's actually solid theorem. If you need to find three variables, you need three separate equations. So we're going to use three equations here, and I'm going to color code them. And the other thing I'm going to do here is I'm going to change, I'll do this in blue right down the middle. I'm going to change my years. I don't want to enter huge numbers into my t. So we're going to say this is year 0. This is year 1. This is year 2. This is year 3. This is year 4. All right. So that if I want to look at 2014, right? If I want to look at 2014, then I'm going to have t is equal to, what is that? 9, right? Because that's 9 years, right? 2014, t is equal to 9, right? 2012 would be 7, 2013, 8, yeah, t9. And so this makes it easier. We don't have to put these big numbers into our t. All right, so I'm going to pick three values. Any three values will do. I think I tried to spread them out when I worked this. I worked this before I did this one because it has a 0, which will help us out a lot. I did this one because I thought 0.40 was neater than 0.21. And then to cap the other side of it, I did the far end. And so I kind of picked three data points that spread across the data. Oh, that way I wouldn't bias any of these things. But we have our logistic model. So we're going to need to work these. So we're going to solve for A, B, and C so that we can take our logistic model and actually have something where we can predict the future. And we're going to notice we have an exponential embedded in a denominator. All right. So my first equation for A at time equals 0, which is A is 0.05, is equal to C over 1 plus A to the e to the negative bt, or b times 0. But what's nice is b times 0 is 0. Anything to the 0 power is 1. Or 1. And so I get c over 2. Oops, no, hold on. I get c over 1 plus a. Whew, sorry, one of those days. C over 1 plus a. Anything to the 0 power is 1. A times 1 is a. So I can rewrite this equation as 0.05 equals c over 1 plus a. In fact, I'm going to cross multiply. I'm going to multiply the denominator here by this, so I get 0.05 times 1 plus a equals c. And I'll distribute this across. 0.05 plus 0.05 a is equal to c. And so now, if I find a, I will know c. Couple things to note about this. This happens in logistic equations. When time equals 0, the b value does not matter. I have created an equation without b in it. That's okay, my other ones will. And so this will be equation 1. Right here. This will be equation 1. And we'll use this later on to help us out. All right, let's work on equation 2 then. And so that's here. And so I have A at time equals 3, which is equal to 0.40. So I have C over 1 plus A times E minus 3B. E to the minus 3B. I don't know B, I don't know A, and I don't know C. So the best I can do is I can clean up this equation a little bit. I'm going to cross multiply again. So I'm going to get 0.40 times 1 plus A e to the negative 3b equals C. And I want to distribute this. 0.40 plus 0.40 A e to the negative 3b equals C. And this is equation 2. All right, and for equation 3, I'm going to use my time equals 6. So remember, I have 3 variables I don't know. I need 3 different equations. I've got data. I'm putting my data into my model, and I'm getting 3 separate equations that I'm going to unify slowly. So A at t equals 6. All right, well, my value, let me scroll up a bit. I just lost the end of that. Was 0.85 equals C over 1 plus A e to the negative 6b. I'm going to cross multiply. So I get 0.85 times 1 plus A e to the negative 6b equals C. And I'll distribute this through 0.85 plus 0.85 0.85 A e to the negative 6b equals C. All right. And that's equation 3. Sorry. I'm scrolling up. Make sure I have each of the things in here. When I did this earlier today for the other class, I dropped a 0 in the last three steps, which put me off a little bit, but we got there. And I want to make sure that I'm not dropping anything here. So we definitely have a value relating A to C and C to A. That's good. All right, so we can, on any of these equations, get rid of C. And we can simplify what we're going to be looking for on these equations. So for number 1, since it says, hey, C is equal to this, I'm going to drop number 1 into number 2 so that I have no C values. And I'm going to drop number 1 into number 3 so that I have no C values. So I will have taken, I don't know A, B, and C, but I do know how C is related to A. So I will not worry about C in equations 2 and 3. I'll replace it. And this is going to look like this. So let's see, I want to do the blue. I'm going to take number 1, and this is blue equation, 0.40 plus 0.40 A e to the negative 3b equals, and instead of the C, I want to write this, 0.05 plus 0.05 A. Now I only have 2 equations, or 2 variables to deal with. I have A and B. I don't have 3, I have A and B. So I need one more equation. That other equation is going to be 3. So what I'm going to do here is that for right now, I'm just going to clean this up a bit. I'm going to get all of the numbers on one side and all of the variables on one side. And this is kind of backwards to how I want to write it. I want my numbers to be positive. So I'm going to subtract 0.05 from 0.40. That's going to give me 0.35. Right? I'm subtracting this from this. And then, well, let me just do it. I'll do each step here. 0.35. So I've subtracted this constant from both sides, and that leaves me with this. I'm going to subtract this from the left-hand side, so that on the right-hand side I have 0.05a minus 0.40 a e to the negative 3b. I'm going to do a little, notice that both of these have an a. So I'm going to pull the a out front. And it's going to leave behind 0.05 minus 0.40 e to the negative 3b. Well, I'm going to divide both sides by this. And I'm going to write my a on the left-hand side now. So I get a is equal to 0.35 over this. The 0.05 minus 0.40 e to the negative 3b. And so I'm going to call this 2 star because it came from equation 2 and I simplified it by substituting in c. I'm going to do the same thing with equation 3. So again, our goal is we have a logistic model. We know our population is growing and decaying, and our population, our cell phone subscriptions in India, people are buying more and more and more and more, and the market starts getting saturated. Saturation of the market means the market can't support as many subscriptions. We're reaching, the number of people to buy subscriptions that don't already have it is dwindling. And so your supply and demand chains, you start peaking out your curve. We have a logistic model. We have 3 variables in our logistic model we need to fit our data to. So we needed 3 data points to match. That generates 3 equations. And so we are solving for those 3 variables in those equations. So I'm now going to take equation 3 and I'm going to use this definition for C in equation 3. So I guess I'll switch back to red, come down here, and I'll go 0.85 plus 0.85 a e to the negative 6b equals, and I'm going to go all the way back up to equation 1, and I'm going to grab this. We've hit the worst part of this. Once we get this arranged, we will be able to get this down to 1 variable. And once we get it down to 1 variable, once I find A, I can find B. Once I find B, I can find C. Or it's actually the other way. Once I find B, I'll find A. Once I find A, I'll find C. But we're almost there. And it's the same pattern after pattern, doing the same things. Well, I'm going to do the same thing. I'm going to subtract 0.05 from both sides, and I'm going to subtract 0.85e from both sides. So I get 0.85a minus 0.85a e to the negative 6b. I have both of these have an a, so I'll pull out the a, and so I get 0.05 minus 0.85 e to the negative 6b equals 0.80, and I'll solve for a. So a equals 0.80, this, right? A equals, I divide that by both sides. 0.05 minus 0.85 e to the negative 6b. Oh, and that's 3 star. But notice what's nice about 2 star and 3 star. This is A, and this is A. If I have two things that are both A, they're equal to each other. And so, yeah, I'll use bright yellow to make them equal. I'll do that. I will say that 2 star is equal to 3 star. So 0.35 divided by 0.05 minus 0.40 e to the negative 3b is equal to, right, because that's A. So wherever I see A, I can replace it by this. So I'm replacing it into here. 0.80 divided by 0.05 minus 0.85 e to the negative 6b. Look what I've done though. I started with an equation that had 3 things I didn't know. A, B, and C. Now, I have something that only has B in it. It's the only variable I have. So I'm going to solve for B. These are the best models we have. Yes, they're hard. Yes, this is hard. But each step is a small step. We're just climbing lots of them. The only big step's coming up in a second. So I'm going to cross multiply 0.35. Right, I'm going to multiply this with this and this with this. So 0.35 times 0.05 minus 0.85 e to the negative 6b is equal to 0.80 times 0.05, this stuff down here, minus 0.40 e to the negative 3b. All right, we're going to distribute, and then we're going to get everything to one side of the equation. We're going to set this equal to 0 so that we can use our factoring rules. But actually, I'm aiming for, well, you'll see what I'm aiming for. All right, so calculator time. Let's turn on, get my lights on here. It's starting to get dim. All right, get the light on up there. Sorry about that. So 0.35 times 0.05 is 0.0175 minus 0.35 times 0.85 is 0.2975 e to the negative 6b equals 0.80 times 0.05. So I'm distributing. Right, I'm distributing to each of these things. It's 0.04 minus 0.80 times 0.40, which is 0.32 e to the negative 3b. Okay, not too horribly bad. I'm going to bring everything over to the right hand side. So I'm going to subtract everything from the left hand side. So this is going to be 0. I'll subtract everything from here, and I'm going to bring everything over to the left. So I get 0.2975 e to the negative 6b minus 0.32 e to the negative 3b, because that's already over there. And I'm going to subtract this from this. So 0.04 minus 0.0175 is positive 0.0225. I want to stare at this for a while, because my job here is to get b down from the exponent to solve. So how do I get this b down? Right? And no, it's not the B movie or anything like that. But notice, this is twice that. And I warned you that this pattern might pop up again. I could do something silly. I could say, hey, why don't I make this represent e to the negative 3b? Just make some other variable represent it for right now. Well, if I squared it, that would be e to the negative 3b squared, which is e to the negative 6b. Hey, but I have one of those right there. What does that do to this? This deserves a different color. This deserves a different color. This deserves a purple. Well, let's put these in. 0.2975 e to the negative 6b, I'm going to call it u squared, minus 0.32 e to the negative 3b, well, I'm going to call that u, plus 0.0225. That's the quadratic equation. I can do things with that. In fact, I can use the quadratic formula, which we will. So u equals 0.32 plus or minus 0.32 squared minus 4 times a, 0.2975 times c, 0.0225. All over 2 times 0.2975. There was a way out of that hole. And that was making this thing look quadratic. And the book goes over this with a whole bunch of examples in logarithmic and exponential equations of using quadratic forms. We've used quadratic forms before. I don't think I've ever gone through a logistic model without being able to get a quadratic form out of it. And one of the things to look for when picking your t times is to try to pick doubling lengths, because doubling works really well for it. All right, so I'm going to try my calculator version here. 0.32, I want to do the addition first, plus the square root of 0.32 squared minus 4 times 0.2975. Oh, did I forget my square root key? No, I did not. Good. 2975 times 0.0225. And that gives me upstairs 0.595, which I think is exactly what I get downstairs. 2 times 0.2975. Yep, is 0.595. 0.595. So one of these answers is u is equal to 1. Did you think that would happen with all these decimal places? You would get an exact 1 coming out of it? There's a reason for it, but it has to do with domains and such. That was you doing the positive. So I'm going to scroll back up and I'm going to do the negative. So that's one of them. And so for the negative one, when I mean scroll back up, I go back up on my calculator so I don't have to retype everything in. Except for some reason, my memory is full on my calculator, so it's not letting me scroll back up. All right, 0.32 minus second square root 0.32 squared minus 4 times 0.2975 times 0.225. Did I type in wrong? 0.32 squared minus 4 times 0.2975 times 0. I always forget that 0.225. There we go. And that's 0.045, and I'm going to divide that by the 0.595. Yes. And the other value this equals is 0.07563. And approximately. All right, so we've gone through a lot of work. I'm going to do a little bit of a review because, once you kind of crack a hump in a problem, you're going to find the next steps seem to fly, almost disappointingly so. And I just want to talk about the work that we did. So we have data that we're looking at having a logistic equation. Our logistic equation has 3 variables. So we need 3 pieces of data. Try to pick a doubling time in there somewhere so that you can get the quadratic form later on. But we noticed, and that confirmed it was a logistic equation for us, because it was increasing quickly and then it slowed down. So we picked 3 data points and we set up an equation involving the 3 variables we don't know, A, B, and C. The first point we picked was the 0 time. So in that equation, equation 1, the B constant does not get involved. And then we picked a doubling time, a t equals 6 and a t equals 3. And I picked doubling times for many reasons. One of them is I will always get a quadratic equation out of them, but also doubling time is how we tend to measure things. So I picked the 3 and the 6. All right, so we simplified all the equations so we could get them in terms of one variable, which was b here. But because this was not in a form where a variable could come downstairs, we used a substitution to make it quadratic in form. I think I did a couple quadratic in forms when I was still standing in front of you in a classroom covered in chalk dust. And so now I know u is 1 or 0.075363. But u is equal to e to the negative 3b. So I can say e to the negative 3b is equal to 1. And e to the negative 3b is equal to 0.07563. Well, the things we want are b, c, and a. So I have to work here. Well, I can use my ln. So if I take the natural log of both sides, the bases cancel, and that gives me negative 3b, and the natural log of 1 is 0, so b is 0 for one of my answers. Well, if I come back up here and look at my logistic equation, if b is 0, that gives me the carrying capacity back. It throws me out to this full state where it has chomped off any value over there. Or not the carrying capacity, but the c over 1 plus a. And so it gives me a point that isn't a value to me. So the b equals 0 is not an answer that we're going to take, but we'll take this other side. And so ln e cancels, leaving me with negative 3b equals the natural log of 0.07563, or b is equal to ln 0.07563, all divided by -3. Well, that's a calculator moment. And in this moment, my calculator says, nerds. No. The natural log of 0.07563 divided by -3 is 0.861. 0.861. 0.861. All right, ready for mass disappointment here. We've just done a lot of work. We've done a lot of really good work. We have used everything we have done all year to simplify it, and we've got one of these equations. Now everything's going to go really, really weirdly quickly. So I have B. It'd be really, really nice if I had A. So I'll pick this equation here. A equals 0.35. And so I'll say A equals 0.35 over 0.0005. All right. I'm so excited it goes quickly and excitingly that I'm typoing. 0.05 minus where do I have it here? 0.40 e to the -3b, but I know b now. Right? I know b. Let's see if that's right. Just quote this again. A is equal to 0.35 divided by 0.05 minus 0.40 e to the -3b. A is equal to 0.35. Told you, once we get one of these, the other ones fall into place. Well, this is a calculator game, right? So let's just use my parentheses correctly on my calculator. 0.35 divided by parentheses 0.05 minus 0.40 times e, so that's second ln, -3 times 0.861 parentheses. I missed, let's see, did I mistype something? 0.5 negative 0.40 e to the negative, yes I did. I typed in a 9 instead of a 6, there we go. That's much better. I get 17.69 for A. So we go through all this work, we get B, and we're one calculator step away. And my word, massive disappointment now. All the work's gone, and we just have to plug in because all the way up here, equation 1 said that's going to be C. So I'll come back down here and go C is equal to 0.05. Nope. I'm saying it one way, but I'm writing it the other. 0.05 plus 0.05 times A. And we know what A is. And so C is approximately, calculator fun, 0.05 plus 0.05 times 17.69, 0.935. Well, let's put all of this back into what we wanted, our model, which is this right here. So I have my amount as a function of time equals C, which is 0.935 divided by 1 plus A, 17.69, times E to the negative bt. So negative 0.861 t. And we now have our equation where we can predict for years after 2005 your cell phone service in India in billions, right? Because that's in billions. Yeah, it's hard. It's not impossible. Every step in there you've done, but we've put them all together. We've solved. We've had to use our logarithm rules. We've had to use our exponent rules. We've had to use substitution rules. We had to use the quadratic equation in the roots. But it all comes together. And logistic equations and carrying capacities are probably some of the most used business and biological equations, right? All right. That's it. That was the last thing I wanted to show you. I wanted to show you the rules of algebra, and I wanted to put it all together in the logistic equation in one thing. If we would have been in class, I would have given you one of these. We would have sat down and we would have fought with it afterwards. But you guys have plenty of practice on Pearson to work through. If you need anything, email me. All right? There's no second half for today. If we would have been in class, I would have been having you just take a test today and then run away screaming for joy or sorrow or throwing things at me. I hope to see you all soon. Be well, be safe. I miss jumping up in front and down and you covered in chalk. Doing the best I can with the tech here. I think if I would have had more time to plan, I would use the tech slightly differently. And now that I have a camera, right? Now that I have a camera, right? A lot more like chalkboard me. Right. But anyway, thank you. It's been a fun semester. In spirit, email me if you need anything. Please be safe. Be well. Hope to see you all soon.